Okay. Hello everyone, so we're going to start. Thank you for being here with us today to this new conference of the AIM Institute. So I guess you already know who we are, what we do. Very briefly, the AIM Institute is about the impact of artificial intelligence in value creation, in new business models, how it impacts work, organizations, and governance. We have different actions around research, but also around pedagogy in module certificates that we want to deploy within the school. But we also have this kind of outreach lectures with experts in machine learning, in computer vision, in language processing. So the idea here is to bring you an accessible understanding of what are those technologies behind AI, artificial intelligence. And the opportunity here is to really welcome people involved in their daily work as researchers and experts in those technologies to interact with you guys and explain, if you are a student, faculty members, members of the staff, or anyone outside of the school and partner, to learn more about those technologies. So we are happy today to have with us Christian Wolf, who's a member of the INSA Lyon, also a professor of computer science and computer vision at the CNRS lab LIRIS. You are an expert in machine learning, in computer vision with a specific focus on complex scenes in motions, so we'll see that. You've been involved in many different projects, national and international, in relation to image processing and vision. You are also a member of different groups, research groups in France and outside of France on those very specific topics. And you are also a supervisor of PhDs. I think you got, 10 PhDs already supervised under your leadership. So thank you for being with us, Christian. Your talk is about vision. And now the floor is yours. Thank you.
Thank you very much. Thank you very much. Thank you for the invitation. I'm very happy to be here to present the work of my students and myself on this topic, and also about the community in general. So it will not only be our work. I will talk about vision, and I will start immediately with a slide which shows. Oh, right. Okay. Which shows a typical problem in computer vision. So computer vision is the science of basically understanding images. You take images, these images can be taken by your smartphone, a camera installed somewhere like this camera here, on a drone, on a robot, on a DSLR, and you want to understand the content. And here you have latest work from one of my ex-students, who is now at Facebook, where you see people in images, and this algorithm here, learned algorithm through AI, is capable of detecting people, so finding where they are, and also detecting their dense pose. So these little points which you see here are points which show that the algorithm understood that each pixel has a specific position parameter in parameter space in the human body, and can say, for example, this pixel belongs to the knee, this one to the shoe, etc., etc., etc. So this technology can be used for various purposes, which we'll talk afterwards. So this is a typical problem where you go from images to some kind of semantic space. What do we see in there? Detect objects, detect people, detect their pose, their intentions, their emotions, their activities, their gestures, etc., etc. So how do humans do that? Because humans are perfectly capable of doing that. Well, we have a couple of organs for that, and one is the eyes, but the eyes is not with what we see. Eyes are sensors, and they produce images. Seeing is done up here in our brain, in the neurons, which need to understand what the eyes actually delivered in terms of information. So if you leave your bed in the morning and you start to take your breakfast, you will see something like this. If you are in America, because this is where they have this kind of orange juice bottles, ours are a little bit different. But anyway, so this is a typical scene from egocentric view. So your eyes could see that, right? And this is how your brain sees that? No, not really. Well, this is, yeah, how you see them, but in reality, this is what your brain gets as raw information, right? An image is basically a matrix where each value here corresponds to a point. The point is, for example, this value here is high if it's close to white, it's low if it's close to black. If you see color images, then basically have three values. Why three values? Three primary colors, red, green, blue. And the task of the brain, and if it's an artificial person, so an algorithm, the task of the AI is to interpret that. So to find out that this amass of pixels here corresponds to the scene we just saw. So this is a really highly complex process which uses lots of oxygen and energy. So just to give an example, a fighter pilot which controls its plane, when it does extreme maneuvers and loses blood pressure, the first thing he loses is vision. It blacks out. Because this is the first, this is in the more, the vision process basically takes an enormous amount of energy by the brain. So why, if it's so complex, why did we get it? Well, evolution gave it us to you, because in evolution we got a competitive advantage if we were able to decide to run in this kind of situations, or to smile in this kind of situations. So this was an enormous evolutionary pressure which made us develop high-level cognitive processes like vision and others. Also, for example, is this something interesting here? Can I see this? Did I see this tree before? Well, I did see this tree before. It is not far from my cave. Perhaps I should turn left behind it, and then I'm back home. So, understanding friends, understanding dangers, finding my way through the world. This is what computer vision gave us as a competitive advantage in terms of humans. The problem is now, can we do similar things in industrial settings, in industries, in any industrial problem, robotics, for example? Yes, we can. It's just complicated. We need to work on that. It's not immediate. So a couple of applications where computer vision plus AI is used in industrial settings. So this is a car from the Indra team where I'm on leave this year. So this is a car equipped with sensors. So you don't see all of them. There are a couple of sensors here. There's a camera in here. And there's a radar in here. And from this video and LiDAR streams, when you drive, you can get this kind of information. So this algorithm here is a video shown from the front camera. And the colors here, the false colors you see, are already the result of the computer vision algorithm. So if something is, for example, pink, it's a sidewalk. If it's red, it's a pedestrian. If it's blue, it's a car, etc., etc., etc. So this thing has been learned, machine learning. So basically, this means that from 5,000 images, people have been asked to take a paintbrush and paint the picture and paint over sidewalks, pedestrians, etc., etc., etc. And these supervision signals, we call them, we supervise an algorithm to imitate pure humans. And the neural network, the AI process, is capable of learning how a car looks like, what is a car, what is a sidewalk, etc. So this is an example of supervised learning, but I don't want to create the impression that all learning is supervised. So we can have smart processes which do not imitate humans. It's just easier for researchers to supervise algorithms, and so that humans show an algorithm what to do, but it's not necessarily done always. Another application is human-robot interaction. So this is an industrial project done with the Avobot company and a couple of other research labs. So this is the robot of Avobot at the NVIDIA stand at one of the NVIDIA's conferences. And this robot is capable of recognizing gestures. So it has a small 3D camera up here, a Kinect, for those who know that. And basically, when you perform communicative gestures like turn around, etc., etc., it is able of understanding that. And this software was developed by our lab. It looks like this. So we first detect key joints of the human body. That's Microsoft, which does that basically. It's not our work. And then from a huge data set of roughly 14,000 gestures, we train a model, a neural network, to understand new gestures. So these are Italian gestures. This is the name of the gesture, prendere. If it's green, so this is the real name of the gesture as identified by the human, and this is the recognized. Oh, this is okay. I'm going back. Another. Okay, I will be able to do that at one point. I don't know what happens, but the video doesn't play anymore. Here it is. If it's red, the first one is red, it's wrongly detected, so there's a small mistake, and then it's all green. If it's green, it's correctly detected. So this is the recognized activity. And this, again, is done from machine learning, right? Learning. Instead of hard coding rules of what your hand motion needs to be, we learn these gestures from a training data set. This is articulated pose estimation, where we train algorithms to find out where exactly are the different joints of the fingers, for example. This is something you might need if you work in VR applications, virtual reality, for example. You would like to take a mask, a VR headset, and you would like to take an object, turn it around, and identify this object has not been made yet. There's a 3D model of it. It has not been 3D printed yet, and you would like to see it. So you turn it virtually with your hand around, and for that the VR algorithm needs to know where your fingers are, so that such that it can render you the position. And this is where we need this kind of technology. It would be very complicated here to hard code rules to say that, yeah, if this pixel looks like this way, if the neighboring pixel is red, the other pixel is green, then this is the tip of the finger. This would take an enormous amount of engineering to come up with these rules, and even then it would not be optimal, it would not be very robust. So these kind of algorithms have been trained on large amounts of data. The problem is, this data at some point needs to be generated, right? In the other example, we used supervision in a sense that people have been asked to paint training images. And here it's very complex to ask people to say where the joints are, because sometimes they're not visible or they're just hardly visible. And we want the algorithm to be better than humans, right? Humans have a trouble to find the joints here. We want the algorithm to find joint positions where humans can't provide them. So what we do is we train partially on synthetic data. So you have two different types of data. Oh, this has been moved around. This should be somewhere up here. So we have parts of real data that was not from us, NYU, New York University. They put markers on fingers, and during the training phase they have the position of the joints because there are markers on them. But you can do it only in a limited amount, because basically people need to put these markers on, need to perform gestures, need to have a sufficient amount of people. It's complicated, and the markers also change the shape of your hand if they're too large. So what we did here is we created a large amount of synthetic images where we basically rendered, we simulated 3D hands and simulated data. And on the simulated data, we know the hand position. So we use here computer games technology. These are basically human models which are used for computer games. We use this technology to render data, and then we train it on it. The problem is these simulated hands are slightly different. You can't simulate with 100% perfect fidelity. So you need to model these changes here, this shift in geometry from simulated to real hands in order to make it work afterwards in the real world. So this has been done in this project. So this is a PhD student who went to Facebook after she graduated at LIRIS and INSA. And I'll go back to her current work, which she has done with Facebook, where she took this pose estimation technology to a new level. So basically, this is dense pose, where you don't detect key joint positions, but for each pixel in the image, you detect a U and V value, so basically a 2D coordinate in the human body. You can parameterize the human body and lay U and V coordinates over them, and you can basically regress, you can do a mapping of pixel positions to human bodies. So here he made fun. It didn't work so well in the media. Basically, they took clothes off of people. Not everywhere, fortunately. So basically what they did here is, as soon as you have the key pose, the dense pose, you can say, I replace pixels by other pixels. I map a different texture on them. You can also change the face, basically. So you can take videos of people, the quality is not yet so good. So there is follow-up work, they're still working on it, but you could take videos of people doing something and map different people on top of them, which raises lots of questions. Can be done. What you can also do is, for example, let's say you're interested in buying this dress here. It's just that this dress is in a position which you don't like. So we'd like to see, okay, what does it look like from behind or from the side in a different position? So this is the follow-up paper where basically they first detect the dense pose here. This is the real pose of the image. Then they let the user click on a couple of target poses. In which pose do you want to see the dress? Then they use geometry and learning to produce a new image from the desired pose. You can see, okay, and this can be done in real time. So basically you can even turn the person around and look what the dress looks like just from a single image. Obviously, if the real dress has a different texture at the back than at the front, this will not give you the texture at the back. It doesn't perform miracles, basically, right? So it extrapolates knowledge from one pose to another one. So this is how this looks in real time. So this is this is the image as it has been captured by the video camera. And this is the input image to the algorithm, which is, okay, we would like to have these clothes on these people. Yeah, the quality can still be improved. It's still research, right? So we didn't solve the problem yet as a community. But learning to generate high resolution images works quite well now. So this is a paper from this year, ICLE 2019, was just accepted at the ICLE conference. And these are not photographs. These are generated images. So this is a model which created a wolf just from saying, I need a wolf, okay? We have limited control over this setting, so current research asks questions of how can I change this so I get a wolf, but now I need a little bit a different wolf. I would like to control different things. This is still an open question, but the networks are capable of understanding what specific object classes look like and how you can generate them with very high fidelity. Okay, you can zoom into these images and the textures are really, really looking good. This can even be done from sentences. It works a little bit less well though. So, for example here, yeah, if you see that it doesn't look really good, that's because it doesn't look really good. But we're going there. So basically from this sentence, I would like to have a sheep by another sheep standing on the grass with sky above and a boat on the ocean by a tree behind the sheep. Bam, everything is in there, okay? The sheep are there, the ocean is there, a boat, well, yeah, looks like a bus, but yeah. So this is the current state of research. The question is, how can we get this better, right? But looking at the speed of research lately, we'll be there in a couple of years. We can also try to go the other way around. So instead of going from the sentence to the image, going from the image to the sentence. So this is what is called image or video captioning. So here we have a neural network which looks at images, has been installed on a smartphone here, and which describes in an English sentence here what it sees. Well, this is not a suitcase, this is a bag, but still, I mean, it does a couple of mistakes, but it is working pretty well. Okay, large window in the background, everything is here. Room with the window in the window, well, okay. Black and white photo of a motorcycle. Okay, there are a couple of problems there, so it's still AI, right? It's not 100% right, but it pretty much understands what it sees, understands being a word which should not to be overestimated here in this context. Last thing, I think, is learning to control. And here we go to robotics. Robotics is a whole different level of problems. So here what people did here is they tried to make a robot walk. So they gave a robot actuators in the form of electric motors, which are connected to some kind of articulated legs. And then the problem is make it work, make it walk. Tell it, go from here to there, right? So you can either hard code that, and if you have more than 2 legs, or even with 2 legs, it's really, really complicated. So walking is really, really complicated thing, and humans need roughly a year for that, right? And learning is one thing you can do it. And why do you see this first on a simulated robot and then on a real robot? That's because learning is not what we call in science sample efficient. We need lots of samples, lots of interactions, lots of images, lots of data to do that. And if you learn from images, okay, let's just provide the algorithm with 1 million, 1 billion images, who cares? No, we'll still care because even that is complicated. But if you learn from interactions, learning here basically means yet you send random currents to the motors, you find out what happens, and if the robot doesn't do what you want, it doesn't advance, basically, you can measure that, then you do something else, right? If you do that on a real robot, you need probably a robot for a couple of 100,000 years, or a couple of 100,000 robots for a single year, both of which are not practical. So basically you do it in simulation first, because the simulation here, you can do it in much higher speed than real life. You can simulate in 10,000th times the speed of time, physical time. You just need a fast computer or many computers. And computers are cheap compared to robots, okay? So you have probably heard from Alphago 2 years ago. Everybody heard about Alphago probably. Well, this is the same principle, right? So Alphago, so this is this software program based on neural networks and a couple of other things, which bet Lee Sedol, so the champion on Go, based on learning. And how did this work? Well, it learned from games. So 2 copies of the same agent played each other. The one who won updated its strategy positively, the other one negatively. Now, for learning, they played more games than humanity played before, right? So if you learn playing Go from a real robot, which will need to take real pieces on a blackboard, you can't do that. So you simulate Go playing, and Go playing can be simulated easily. It's just pieces in memory, and that can be done very fast. And that's why Go was solved as soon as we figured out how neural networks work. Robotics is much more difficult. Because in robotics, you either learn with real robots, then you are limited to physical time, or you learn on simulated robots, and then you need to simulate them with high fidelity. So this works on these situations here, where you simulate walking, or robot grasping, where you have an industrial robot grasping stuff. But learning a robot to behave in a home, in a nursing home, and talk to people cannot be easily simulated, because you need also to simulate the people who interact with the robot. So that's complicated. So learning and robotics is currently a hot topic, and we're working on it. There are lots of problems. So machine learning. I'll talk a little bit about machine learning. So what is a cat? That's a good question. You, as a human, were pretty much able to recognize cats probably even before you were capable of saying the word cat. And when you said the word cat, that's because your mom or your dad said, this is a cat. So your mom and your dad gave you what we call supervision signal, cat. But before you got the supervision signal, which supervised you only the name of the cat, you already understood the concept of a cat. And you didn't know what cat meant. And how did you understand that? Not through supervision. Supervision would mean if you see this pixel and this pixel and this pixel and this pixel, then it's a cat. It's just that you observed the environment and you found regularities. Regularities in the sense that you always saw the same thing very frequently, something very soft, similar color, similar texture patterns. You discovered similar things which arrived in your life. Then you found out, oh, this is something nice. I like it. I love it very much. And then afterwards, when you were supervised, you only attached a name to it. So most of human learning is actually what we call unsupervised. You discover the world. And only a very small part is supervised, where somebody supervises your learning process. Basically, mostly in school. You get supervision. Out of school, you get not much supervision. So what do we want to do when we use learning for computer vision or anything related to images? We would like to take decisions. So here in the first 4 examples, we have images as an input, and as an output, we either want to classify them. So this here is what? Well, it's a cat. Given that this is a person, what is the age of the person? So this is a classification problem. This is a regression problem. Here, for those who don't recognize the scene and who didn't live the 90s as me, this is the Doom computer game, where basically you need to run around the labyrinth and take decisions, go left, go right, pick up this object. Lots of learning in computer science, when you learn to control, is now based on computer games, or at least computer game technology. Why? For the reason I just mentioned, it's very complicated to simulate robots. So we use computer games currently as proxies to learn agents to solve problems. The hope is that our games, you could call them serious games if you want, our games get more and more complicated, and currently we're trying to build, the community, build simulators for robots. So each year there are at least 10 new simulators which get more and more real simulating robots, and which can be run on 10, 12,000 frames per second for learning. So robots simulated in high speed. Here, robot grasping. So this is a real robot. The question here is, can you install an industrial robot which is smart? Industrial robots currently are not smart, so basically they create motion, they do motion which has been programmed by hand. Put like screws in here in the car in exact the same order which we showed you. The dream of any car maker or any industrial producer would be, I buy a robot, I talk to him in language, say, okay, you are placed here, cars are coming here, and whenever you see a car, you do this and this and that, and from language, the robot understands what it needs to do. So this is the dream. We are far away. But we are working on this. And part of it is already just being able to take an object in any pose, not break it, and performing a task. From not programming it, just from experience. So we have robots here. I don't know where I took this picture on, but for example, Berkeley, University of Berkeley in California, has a whole fleet of robot arms. They 24 hours a day, 7 days a week, they just try to poke objects, take objects. When they can take them, they know that, because basically the arm is heavier, right? So when you take the object and you can't, you fail. Your arm has the same weight. If you're able to take it, it is heavier. So you understand that you succeeded. They just randomly take objects. Whenever they succeed, they know they did succeed. They update positively their model. If they don't, they do it negatively. And they learn. Need lots of them. Learning is currently the way to do these things. So how is learning done biologically? Neurons. Inputs to a neuron, which is a cell, and outputs are connected to other neurons. Basically, these connections here store the knowledge we have. Input comes either from a sensor or from another neuron. How can we do this? We have lots of them. You have 86 billion neurons, which would be in français 86 milliards. We have trillions, billion connections, and we only need 25 watts of power for that, whereas this is more powerful than a supercomputer, which needs half a nuclear reactor to be currently needs more than half, needs almost a nuclear reactor to get power. So how does this work in computer? Well, we have these deep neural networks. The same thing basically. It's just that this is not silicon. This is just a representation in our computer memory. This is a value. We get an input value. This could be an image, for example. And this value here is a virtual neuron. It's just a linear combination of these values here. So this value is this input times something plus this input times something. And this times something are parameters, and this is where the knowledge of my neural network is stored. I can predict something here. I think I have an example at Plumplace. No. For example, these 3 output neurons here would be predictions of, is this image here a cat, a dog, or a motorcycle, right? And whenever I put an image in here, these values will be calculated, and the model predicts something. Now, if these values in here, represented by the lines, are parameters, and I initialize them randomly at the beginning, then it's like a baby which is born and which doesn't know anything, right? So what I do, I need to train this model. Training means I let it calculate its prediction. I calculate the error through supervision. It said, oh, this is a dog. And I told him, no, it's not. It's a cat. Calculate this error. And if there is an error, update these parameters such that next time the error is smaller. Mathematically, for those who know these kind of things, is you derive the error with respect to the parameters. You get a gradient, and then you do gradient updates. And you do this repetitively over millions and millions and millions of images, and this is how it works. So these neurons are organized in layers. First layer, second layer. Here we have one hidden layer and one output layer. In reality, we make them deeper. 2012, which was the big breakthrough of deep learning, brought us AlexNet, which is an 8-layer network, which at this point won a huge image processing competition, and which immediately, almost in a couple of months, made the computer vision community switch over from the older models we used to deep learning. So this was really, really fast. 2012 is really a turning stone where the community figured out, okay, everything we did handcrafting and hand coding rules until now, this is not optimal. We shouldn't do this anymore. Let's switch over to learning. And learning all this from large amounts of data, since then, now 2019, completely dominates computer vision. So we have now neural networks which are up to 150 layers or more. To make this train, it was not sufficient to just add layers. Adding layers alone doesn't work. So we needed to find mathematical things, tricks, which made the models train with this many layers. And then you can find out what the knowledge is. So basically you train these things, you take GoogleNet or ResNet, you train it on 1 million images to detect images, to detect objects, you say, okay, how does it work? Where is my knowledge? It's buried in roughly 20, 30, 40 million of parameters, but these are so many. How can I know how it works? Will it work always? Well, you can try to visualize these things. So what do you see here? This is the first layer. This is AlexNet. AlexNet is a small network, has only 8 layers. And here you see layer 1 and layer 2. And what do you see? Each 3x3 block is a single neuron. It's actually a single filter, but it's almost the same thing. So what you see, these are a couple of images. A couple of images to which this neuron strongly reacts. So you get a positive firing from this neuron when it sees these images here, or these image patches. These are parts of images. So in the first layer, you get lots of neurons which detect very simple geometric things like colors, textures, stuff like that. Second layer, the second layer takes these activations and combines them. And here the patterns which these different neurons detect are a little bit more complex. So we have this kind of almost, this texture-y thing here. This is again a color and different textures. These are corners here, rounded shapes, etc., etc., etc. If we go up to different layers, we see that these textures will be getting more complicated. So here we almost have a wheel or tire detector here. Yes, this looks like an neuron which fires with people, right? What is this? Don't know. Minerals. And if we go even higher and even higher, well, we get neurons which fire at dogs, at women, at keyboards, very high-level semantic concepts. Each layer takes the preceding layer, combines it, and makes it more complex. And this is discovered, right? We didn't put this into. No engineer said, I would like to have a neuron which detects dogs, right? But it discovered dogs because one of the classes on which we trained it to predict is dogs. So it discovered this. So we have now this convergence. I said computer vision, the community switched over to learning, to training, and we ever since now use deep networks in priority to solve problems. We use other things as well. But all these low-level tasks are solved with learning, and we're not the only ones. So roughly at the same time, other domains switched over to learning. So traditionally, these 3 domains were different. So computer vision is the one I'm talking about, taking in images and understanding them. Then you have speech recognition, recognizing people talking, recognizing speech, and neural language processing. And they traditionally use different mathematics. Computer vision was dominated by geometry and signal processing, speech by signal processing, NLP by linguistics. Well, we all use now deep neural networks. And you have people like me in computer vision, we start to read papers in NLP because they give us interesting ideas, and they read ours. And this is something really new. And so the trend, this question of, is the human the best designer of a solution, has now been shifted. The solution of this has now been shifted over to, no, he's probably not. And this makes lots of people uneasy because lots of researchers were really fond of designing algorithms, we still design algorithms, but we do not ask questions anymore, what kind of features do I need to calculate on data? So these low-level questions, designing input representation, designing decision rules, this has now been largely removed from our research, and we do other stuff. This is good news for me. People like me love that. Whenever you make people, you remove jobs from people, well, these people can do other jobs, right? And in research, it's the same thing. So we do now other things. But it's not everybody's happy about that. And it's not completely a new phenomenon. So the proof is this quote here from 1988. Every time I fire a linguist, the performance of my speech recognizer goes up. So this is a little bit provocative, of course, but it already shows that 30 years ago, people started to doubt that humans, so in this case linguists, are the best people to design a problem, even in linguistics. And the proof now is that if you connect to Google Translate and you translate, Google Translate now works really well, not as good as a human translator, but reasonably well. I can sometimes take 4 or 5 paragraphs, put them into Google Translate, I get a result, and I don't change a word. This has been done without any linguistics. So Google just took billions of phrases, supervised with translations, and basically Google learns, the algorithm learns to translate just from seeing translations. And it discovers syntax, grammar, etc. You don't need to input it. You don't need to hard code, you need to teach it that, it learns it from data. And now since then we have other areas, databases, computer networks. So I'm this year on leave in a laboratory which does computer networks, and my colleagues there learn how to make computers send data faster and with more security by protocols which are not designed by humans, but learned from interactions. So they put neural networks on computer networks and update the protocol from the result they get with the current protocol. It's learned. So this is, I think I prepared a couple of slides on a couple of techniques, but I'm not sure this is really the thing which is the most interesting. So basically what I wanted to say here is how can we train all this? Well, there's lots of mathematics, but I will not go into details here on that. Then one of the things we do is throw large and insane amounts of data at the problem, right? Pose estimation is now dominated by this kind of installations where you have a couple of 100 cameras here. They look at people, film them, people perform motion, and all this data, which is in terabytes or petabytes, is then used to learn algorithms, detect activities, right? We throw insane amounts of data. Before we used lots of know-how in terms of mathematics, how to do things. We still do that, but it's now accompanied by really large amounts of data. We use all available information from the data. Okay, I will speed up on this part. This is the famous cake by Yann LeCun, but I will just provide this Jeffrey Hinton quote. The brain has about 10 to the power of 15 synapses. Synapses are the connections. Okay? And we only live for 10 to the power of 9 seconds. So we have more parameters than data, right? So this motivates the idea that we must do a lot of unsupervised learning, right? That means for each second you live, you need to learn information about 100,000 connections in your brain. You can't do that. You don't get supervision for that, right? Nobody supervises you to connect this 10 to the power of 5 connections per second. So most of our learning is unsupervised by just looking and trying to understand things. And this is what we, the scientists, are really bad at. We don't know how to do that yet. We are going there, okay? Lots of research is done, but the easiest solution is still supervised learning. And I'll focus a little bit more on this part here. Focus is the right word, actually. Learn to focus on the relevant parts of the data. So this means when we have complex questions, like here, this is an input image, is Paul in the room? How would you address these questions? I suppose you know Paul, right? Let's say Paul, you know how it looks like. You would not like look at the image, not move your head and just find out, is he there, is he no? You would, of course, go from one face to the next and check whether the face is Paul's. You would like scrutinize your image, right? This is called an attention model. Humans do gaze patterns. They gaze on the image. And depending on what you looked at and the result, you will derive the next gaze pattern. So that's what we do now in computer vision. So this is a model from one of our colleagues in Paris. So this is a problem where you have a question, an image, and you need to answer the question. What is sitting on a desk in front of the boys? Well, it's laptops. And what are on the shelves in the background? Books. And here you see what is called a heat map. Red, colored in red, is the area in the image where the neural network decided itself to look to answer the question. This is called an attention model. And the thing here is that this attention mechanism has not been trained in a supervised way. So when my colleagues have trained this model, as a supervision signal, they only gave the answer, laptops. So when the model answered wrongly and said something else, no, it's laptops. You should have said laptops. It's the only thing. And the model learned itself without any supervision. Okay, actually, if I see this, looking at these things here is better. So it discovered the attention strategy itself. This can also be done for activity recognition. So this is work of my group, where if people are running and you need to find out why they are running, well, sometimes you need to look at the people. Sometimes you need to look more at other stuff. So for example, why is this woman running? Well, this might be a clue. Why are these people running? Well, they probably want to catch their airplanes. So we have these algorithms where we train attention models to look at specific portions of a video to find out what happens. So the problem here is activity recognition. What is this person doing, right? And the rectangles here are the areas in the image where the attention mechanism said, look here, this might give you a cue. And when the video starts, right at the beginning, you will see that the person is bending down and immediately the system captured, okay, is he really going to bend down? Let's look at what is in front of him. Oh, there's a Coke bottle or some bottle there, water bottle there. Perhaps this corroborates that he will actually bend down. Same here. The neural network learned itself to scrut in this way. Supervision here was provided only on the result. What did you recognize? Same here. So this is work of my current student, Edward. So again, this is Doom here, the computer game. And we want to learn to navigate in an environment. This is a proxy task for robotics, of course. And here the task is a little bit more complicated in the sense that we want it to pick up objects in a specific order. This is not something you need really to do in a robotics environment, but it's a hard task for a neural network. So for example, there are lots of objects, a gray ball, a red ball, a blue ball, and it needs to learn that it needs to pick up the red one before the blue one. We never tell him. We don't even tell him that there are walls, that there are floors. It needs to learn itself that if it bumps against a wall, that it should look, interpret the pixels here as a wall. Everything is learned. The only thing we provide to the agent is feedback, good or bad. If you bump in a wall, -10. If you pick up the object and it's the wrong order, -20. If you pick up the good one, it's the good order, +5. Things like that. But it doesn't know what action actually made it get positive reward. And after training, we get this. So this is complicated. I'll just spend 2 minutes until I'm finished on this. So these are different steps. The system needs to pick up this ball after this one. This blue ball needs to be picked up after this one. Okay? At step 5, it sees the blue ball. It knows that, okay, I shouldn't go there and pick it up. Not good. Will be punished. It learned that. Okay? But after training, we find out that these are neurons here. These neurons are acting like a map. Okay? And we see, okay, these neurons here actually store the position of this blue ball. This is what we discovered. We didn't hard code that. Okay? This is after looking at the trained model. Okay, it looked at, it stored this position. It sees now the other object. It says, okay, now this is interesting. I'll pick this up, but then I need to find the blue ball. I need to check, did I see the blue ball already? And this is what is called the attention vector. It looks in its map and says, okay, good. Here, I saw it there. I should go there and find it. Okay? And here, step 134, apparently it didn't see it yet completely. We see it as humans. It didn't, because it still looks up the position. As soon as it's in full view, it says, okay, I don't search it anymore. I have it in front of me. I can go there directly. So all this is learned. We never told it create a map. We never told it look at objects. We don't even tell it what an object actually is, the concept of an object. I will go a little bit faster over the rest of my slides because my time is up and I spent too much work at the beginning, too much time. I will just want to finish, if I have 3 more minutes, on one part which might be interesting, which is the experimental aspects of machine learning. So basically what I would like to talk about is first a Nobel Prize in medicine, which has been attributed in 2014 to 2 biologists who discovered in the brain of rats what is called grid cells. So what do you see here? They took rats, like these ones, and let them run around in mazes and find cheese or whatever they needed to find. And so they have this labyrinth here, and the rats for weeks only every day do nothing else as run around and search for stimuli like cheese. And this is a single neuron, which the red dots here are correspond. So this is the plane of the different labyrinth. This is the upper corner of the labyrinth, the lower right corner of the labyrinth. And when the rat is here, this neuron fires. If it's here, the neuron fires. So this neuron encodes the position of the rat. And we have probably, rats surely, have these cells for different frequencies, for different phases. So this is basically, for those who know what a Fourier transform is, basically the rat learns some kind of Fourier transform of its current position. And the discovery of these cells has been earned the Nobel Prize. They also have head directions if it goes to a certain direction. This neuron fires. Border cells, if you're close to the border of the maze, this fires. I think rats which do not evolve in a maze will not get these border cells, will get other cells. They'll learn other cells. But anyway. So why is this interesting? Well, it is interesting in itself, obviously. But it is also interesting for AI because in 2018, we discovered the same cells in artificial neurons. So basically, people created artificial rats, basically neural networks, and they made them solve the same problems artificially in artificial labyrinths. And then they checked the neurons, which have been trained by our algorithms. And they found the same grid-like, band-like border cells as in real rats. So what does this mean? It doesn't mean that we're capable of creating rats. That's not my point. But this means that at a very low level, on these very specific tasks like localizations, and in a very restricted environment, artificial learning is capable of confirming some of the learning which has been done by real agents, biological agents, rats. Now, what this has sparked, not necessarily this discovery, but it helps spark it, is communication between neuroscientists and machine learners to find out how we can benefit from each other. And machine learners increasingly look into neuroscience papers to find out how biological agents solve problems, and attention mechanisms are one of these aspects. We checked attention mechanisms because humans do attention models, right? We are restricted to them. So I'll finish here. My conclusion here is that computer vision is currently heavily dominated by learning. It's probably not going away. That's more my opinion than a scientific fact. So I think it will not go away. We now try to find out how we can combine learning with all the things we did before. That's how we can put geometries and structure and lots of things into learning. This is ongoing. But we will not going back and do handcrafting of low-level processing again. This will probably stay learning. The problem is how can we add high-level reasoning into these agents. So for example, humans are capable of doing symbolic processing. You can solve algebra. A human can solve algebraic equations, right? How can we do that? Well, because we learned it, right? The question is, can an artificial agent learn it, or does it make more sense to hard code this, right? And if it learns it, how is it represented in the brain? And here there are clashes between communities which say we can solve symbolic operations, but they are represented by non-symbolic distributed representations in the brain. And there is the other community which says, no, this is not right. We have symbolic representations in the brain. They are probably formed by learning, but processing is done in a symbolic way. And this is not clear yet. Lots of research is necessary here. And the last message, which I already said during the talk, is that there is a convergence in models and applications between computer vision, robotics, AI and machine learning, natural language processing, speech, and control engineering now. And when I say convergence in models, that means that lots of these communities now use deep networks to solve their problems, but also convergence in application is in a sense that we now solve problems which require vision, language, and even robotics. We, also our team, by the way, try to solve problems where a robot gets speech input, needs to convert the speech to text, needs to understand the text, needs to navigate, for example, ask the robot, where are my keys? So the robot needs to understand what is the text, needs to understand the text, needs to understand the concept of keys, the appearance of keys, what do they look like. It needs then understand the fact it needs to search them and navigate. It needs to find them, navigate in the house, come back and tell me your keys are in the bathroom. So this requires speech, vision, robotics, language, everything together. And currently we try to learn models, neural models, which solve this end-to-end. So the same model has a couple of submodules, but basically the error of the question is backpropagated and is used to update all different modules of this single model. So this is the future we are currently working on. Thank you.
Thank you. Thank you, Christian. Thank you, Christian, for those different examples. We have some time for questions. Do you have spontaneous questions in the audience at this point? No? Because I have one. You've been talking about how you can control images with the Facebook example. It can be done for marketing purposes, of course, obviously, so that you can sell dresses or suits or T-shirts, whatever. There is also a huge question about fake news and fake images. Do you see a tendency in your research of the recurrence of this problem about fake images and how this can be badly exploited? And how do you think this should be taken into account and addressed by researchers like you?
Yes, there is certainly potential for that, and the applications which I showed indicated that. In images, it's still a little bit tricky. We don't yet have the quality of creating really high quality fake images where people, for example, are replaced, but we're going there. We're very close. So I suspect this will be solved in, I don't know, 2-3 years. Currently, we have this discussion on text. I don't know if you heard about the OpenAI scandal 2 or 3 weeks ago about the text, the fake text which has been produced, the GPT-2 model. And text is easier to produce, and so basically for those who don't know, OpenAI, an American company with openness kind of attached to its mission by saying we normally whatever we produce, we already will deliver our models with parameters, and we publish everything. It's open data. So basically, they reversed their decisions on one model, which they produced because they thought it's too dangerous. So what happened is they took enormous amount of text, which has been found in books and crawled on the web, etc., 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 and they created a neural model which, from one or two phrases, produces the rest of the text. How did they do that? Well, basically, they gave it lots of text, and they primed it with the first two phrases and asked it to predict the rest. If it did correctly, said, yes, nice. If not, well, you're punished. And then they train. And now what happened is, from a certain amount of text onwards, there is a shift in the quality of the text, and some kind of, and I'm trying to be really careful here, some kind of rudimentary understanding happens. Now, I don't want to be even quoted on that, because the word understanding is complicated, right? But anyway, can I go back to my slides? Can you switch back to the slides? I'll show you. No, that's not what I wanted. Of course not. Here it is. So I'll give you an example. Text, where is it? Here it is. Oh, go ahead. So what do we see? This is an example which has been widely discussed, right? So this is the context. This is the input neural network, and this is what the neural network needed to produce. In a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that unicorns spoke perfect English. Now, go ahead, develop. It's like in high school, right? Develop. Go ahead, do something. What the network predicted is the scientists named the population after the distinctive horn, Ovid's unicorn. These four-horned silver-white unicorns were previously unknown to science. Phrases with full grammar, kind of understanding. Dr. George Perez, an evolutionary biologist from the University of La Paz, blah, 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 blah. Perez and his friends were astonished to see the unicorn herd. Believes that unicorns have originated in Argentina. So what did the network understand? It needed to understand the concept of a discovery, of a new species, that scientists exist and probably teach at universities, and a couple of other things that these species might have an interest. These are the concepts which clearly have been understood, right? I'll put this in quotes because it's unsure what understands here means. But anyway, these are regularities which have been discovered here. There are a couple of mistakes. Did anybody find a mistake in here? You need to look really closely to find things which don't make any sense. Anybody found something? Four-horned unicorns. It's a rare species, right? Obviously, unicorns are not four-horned. Then Ovid's unicorn, after the distinctive horn. Why would a distinctive horn give rise to Ovid, who is a Roman writer? Doesn't make any sense, right? And there are a couple of other these, but basically you need to be really reading carefully to find this, okay? Now, this basically is a statistical model, right? You predict future sentences from past sentences. Now, this raises more questions about us than about this. This basically means perhaps lots of our cognitive power comes from statistics. I don't know, but this makes sense, right? And it's only statistics. So just by predicting future, if the order of your model takes into account long and longer sentences, makes emerge these kind of behavior, it's frightening, right? I don't think this is really a text understanding. Obviously, it's not. But, and now I go back to your original question, which I kind of forgot, apparently. Well, this kind of model can be used, for example, and this is the reason why they didn't publish it. They published the paper, and you can redo the model if you have the data. It costs $100,000. You can just crawl the web and get the data, and implementing the model for an expert is nothing. It's not a new one, basically. The methodology is not new. Nothing new in there. So why didn't they do that? Because you can take a couple of phrases and generate very cheaply at almost zero cost large amounts of data which you can flood into social networks. So if at one point you are a nation who wants to influence another nation, you can produce cheap text and just put it in. You can even create interactive models where these models basically participate in the discussion. So you just lose bots on discussions, political discussions, and they will just create really biased answers for zero cost. It's apparently, and this is discussion, I don't want to go into this direction, but people say it's already done by humans, right? There are rumors, I don't know if they're justified, that certain nations run troll farms. Well, you don't need troll farms anymore now. Yes?
In this case, the network has been trained on newspaper only, for instance, because we recognize the style of more or less newspaper writing rather than novel. So was it training on novels?
I'm not aware of the exact nature of the text, but lots of it was crawled from the web. Books, there are also books, but most of it was apparently crawled from the web. It's roughly 40 gigabytes of text, which is not much, 40 gigabytes, but text in videos, 40 gigabytes is not much. On text, it's a lot.
When you are on the internet, from time to time, when you want to buy something, there is a security operation that shows you an image just to check you're not a robot. When I hear on senior conference, I'm a bit confused because I understand that the machine is so powerful that they can easily see where's the light fire or the traffic light or the bus. What do you think about these security operations? Are they efficient or not?
No. No, my answer is yes and no. So basically, this is a cat and mouse game, right? As soon as a hostile organization wants, these are called captures, okay, wants to solve these captures, it just needs to train a new agent to do them, and there is no inherent, in the captures I saw, there is no inherent problem in an agent getting these captures done. There are still lots of problems because you probably all heard about the Turing test, right? And there is no there's no humans solve the Turing test. There is no artificial agent yet which solves the Turing test. So you cannot yet produce an artificial agent which can fool humans. But this involves mostly conversations which take some time, etc., etc., etc. So just solving a single problem is mostly solved. A visual problem. I wouldn't say it's solved. Okay, you can still create lots of tricky images which are completely not solved by vision. So I don't want to be misquoted on that. But the kind of captures I saw until now are really easy. They are like letters hidden in some texture. These can be solved if you train an agent on them, and it's done.
Any other no? Maybe just to conclude, one last question. You are in a business school today.
Yes.
So it might be a challenging question. How do you think our researchers or our students in business school could use computer vision or could use neural networks or machine learning to the benefit of what they will do in the future? So how do you see the impact of what you've been discussing on the business point of view? And how it would be relevant for our students and researchers and faculty to be involved with those technologies?
Well, I am a fervent fan of AI, and AI has lots of potential. Now, I can't tell you exactly how, I'm not an expert in business, obviously, but there are still lots of unexplored things which AI startups don't solve, and the problem I mostly see is that people underestimate the problems, the scientific problems and the data problems. So I just read an article a couple of days ago that like 40 or 60% of AI startups in Europe don't use AI. In a sense that even they just lie, or they say, I use AI, and in reality it's humans who do the work, and they just collect data, and then they say, okay, later we'll do AI. And then it is kind of, oh, this is not easy. So my message would be, and also from, I'm not sure if this answers your questions, but my message would be, and from my interactions with companies, because we work with companies, is do not estimate the amount of data and effort you need to deploy to get the problem really solved. Because academics will tell you one thing, me included, oh, it's solved. When I say solved, it basically means that, okay, in 97% of the cases you provide the correct answer. For in academics, this literally means it's solved. As soon as on a data set we get even 95, 96% of the answers, we switch to the next one because we get bored. In an industrial business setting, this is not the case, and autonomous cars are the best example for that. So AI is, with the academic eye, extremely powerful. So most academics were completely surprised by what we could do. When I did my PhD 15 years ago, I wouldn't have imagined that 15 years later we would get this kind of models. We were surprised. And then there is this shift between the media on the one side and the academics. And the media either is completely fooled and says, oh, well, now Terminator will take over Skynet, or they say they focus on negative examples. Okay, so this Tesla car killed a man because it went into the truck. And then they focus on the 1 or 2% which don't work. And the problem are these 1 or 2%, right? We, the academics, we're not so much interested. Most of us, I don't say, we're not interested in that. The businesses are, and they have troubles getting there. So learning is one thing, but validating it and making it work on 99.9999999% of the time, that's not done. And I finish with one quote by Andrew Carpati, who did a PhD a couple of years ago at Stanford and Google on video captioning. So the video captioning slide I showed was from him. And he's now the director of self-driving cars at Tesla. And he, a couple of months ago, showed a slide where he said, okay, this is the difference between my PhD and now my work at Tesla. And he showed pie charts. And in his PhD, he was working all the time on mathematics, or at least methodology, and like 2% of the time with data processing and data collecting. And at Tesla, it's all the other way around. So most of the performance you get out of your work in real case business scenarios is data. That's the most important thing. You need to have lots of data, and this is an enormous effort. So this is where the problem starts. So if you want to start an AI startup, the only thing I can tell you, try to be realistic and let's check whether you can reasonably get the amount of data you need to solve the problem. I don't know if this is what you expected.
Thank you. Thank you very much again, Christian. We can maybe applaud you a bit. Thank you for being with us. Thank you for coming to this conference. So we have our next conference, which will be in April. We'll be talking about large-scale networks with Martin Karsai from ENS. You will receive the invitation in the coming weeks. Thanks again for your presence and your interest. And as you've understood, there is many things to be done with AI in terms of application. It's not because 95% of the problem is solved that you can make a product out of it. So that's why in terms of business, we have a huge opportunity. So thank you again. Have a great day and see you soon at the new conference. Thank you.
Merci monsieur.